Hello and welcome to our video on the Munkres assignment algorithm. First of all, the problem. A one-to-one matching needs to be made of the set A to the set B. Each element of the table has a cost function. For example, we have n workers and n jobs to do. And each person charges a certain amount to do each job. As a table, it would look like this. Here is an example of an invalid assignment. And here is an example of a valid assignment, but it's not the optimal one. And this is the solution that we want, the minimum possible assignment. And here it is as a bipartite graph, but we will be using the matrix form. To do this problem, there are some assumptions we have made. For example, there are the same number of workers as tasks. There are fixes you can do to make sure that there are the right number. For example, if there are more workers than tasks, we can add dummy tasks, like this. Each worker does exactly one task, no more and no less. Each worker can do every task. If this is not the case, there's a fix for this, as shown on the slide. And we have access to the complete matrix. We're looking for the minimum, not the maximum assignment. But again, there is a fix for this if we want to find the maximum assignment. So here we have the algorithm itself. And here is a flowchart of the algorithm, showing a high-level description. And to demonstrate how it works, we will work through a standard example. Here is our problem as a matrix. And so first of all, we need to reduce the rows. This means we need to go through each row and subtract the minimum value in that row from every value in the row. And here the first row has been done for us. Then we go on to the second one, and the third one, and finally the fourth one. And next we need to reduce the columns. So this is very similar to reducing the rows. We need to go through each column and subtract the minimum value in that column from every value in the column. The first one is already done. And now the second one's done, and the third column, and the fourth column. So next, we need to cover all of the zeros in the matrix with the minimum number of lines. We'll show you how to do this in more detail later. But here is this step completed. Now, is the number of lines required exactly n? Exactly n lines are required, so we then have to assign tasks. And we need to set exactly 1 0 from each row and each column to being assigned. We'll show you how to do this in more detail later. Now we need to get the cost of the original assignment. And here we have it, and the final solution is 7.
Let's now look at a more complex example to demonstrate some parts of the algorithm which weren't needed in the previous one. So here we have another problem as a 4x4 matrix. To start with, we reduce the rows, just as we did before. So we subtract the minimum value in each row from every value in that row, and that produces the result you can see here. Once again, we reduce the columns, so we subtract the minimum value in each column from every value in the column, and that produces the same result as every column here has a 0 in. Now we come to the cover 0 step, where we need to cover all the zeros using the minimum number of horizontal and vertical lines. This time, however, we find that only 2 lines are needed to do this, which is less than 4. So if we ask, is the number of lines required exactly n, which is 4, the answer is no. So now we go on to the add extra zeros step. To add extra zeros, we go through these 4 sub-steps you can see here. To start with, we find the smallest value which is uncovered in the matrix, which, as you should be able to see, is 1. We set this as k. We then subtract this from every uncovered element in the matrix, which you can see here within the blue box, like so. Next, we add it to all elements which are covered twice, which here is just the 0 in the top left, like so, and we finish by removing all coverings from the matrix. Now more lines should be needed to cover all the zeros, so when we go back to the cover 0 step, this time we find that 3 lines are required. However, this is still less than 4, so we once again go to the add extra zero step, and this time when we go through the same 4 sub-steps, it produces this result. Now, when we try to cover all the zeros, we find that it's not possible to do it with less than 4 lines. Therefore, we can now go ahead and assign tasks. And here is one possible assignment, though there may be, in this case there are, other ways of doing this. Regardless of which one you choose, they will always produce the same cost, in this case 7. And so there we have the overall algorithm. So the question remains, how exactly do you assign tasks or cover the zeros algorithmically in such a way that you will always get the correct answer? There are naturally multiple ways of doing this. However, the technique we used for our implementation was to use one algorithm which does both in one go, but there are naturally other ways of doing this. So here's a flowchart of the method we used, and here it is as a series of steps. To start with, you assign zeros naively. You do that by going through each row and assigning the first 0, which does not already have a 0 assigned, in the same column. You then go and cover any columns which have an assignment in. You now check if there's any uncovered zeros. In this case, as you can see, there's one right here. So you mark it and you label it as x0. You'll see why in a moment. You then check if there's an assignment in the same row as x0. There is in this case. So we cover that row and uncover the column with the assignment in. Then you go back and check again. Are there any uncovered zeros? Once again, yes. So we mark it, and now this one becomes x0. However, this time when we check is there an assignment in the same row, the answer is no, there isn't. So we now go on to the next stage, which is to create a series of x's. To do this, you first pick the element x0 and set that as the first item in your series, which is why we called it x0. Then you repeatedly apply 2 rules. Firstly, if the last item in your series was a marked 0, which it is here, you add an assigned 0 in the same column to the series, if one exists, which it does in this case, right here. If the last item was an assigned 0, which it is now, you add a marked 0 in the same row. One will always exist in this case, and it's right here, x2. Then, because the last item is a marked 0, we go back and apply the first rule again. We look for an assigned 0 in the same column, but none exists, so we are done. So, we now go through our series and unassign all assigned zeros in the series, and then we go through and assign every marked 0 in the series. And then we remove all markings and coverings, and go back to the second step of this sub-algorithm. We cover all assigned columns again, check for uncovered zeros. If there's one, we mark and label as x0, and then we check if there's an assignment in the same row, uncover the column, cover the row, and then check for any uncovered zeros. In this case, we're now done. What that means is that we've now covered all the zeros using the minimum number of horizontal and vertical lines, and if it was possible to have an assignment here, we would have found it, although because there's only 2 lines needed and it's a 4x4, no optimal assignment actually exists. If you'd use this method, then you can skip the assign task step, as you will have done it when you covered the zeros.